Today's presentation is Shale Organic Matter Interaction in Non-Aqueous Drilling Fluids with Dr. Sean Liu and Frank Zamora. Before we get to the presentation, I want to give you a little bit of background for both guest speakers. So Frank Zamora joined Premier in June of 2016 as a Senior Vice President over Fluids and has more than 45 years of experience in the oil and gas industry. And he previously held leadership positions with FTSI, Trican, and Weatherford International. He began his career with Halliburton in 1977, serving in numerous oil field positions there for nearly 27 years. He earned a bachelor's degree in electrical engineering from Texas A&M and a master's degree in engineering technology from Oklahoma State University. Mr. Zamora holds more than 50 industry patents, numerous technical papers, and is a registered professional engineer in the state of Texas. Now, give me 1 second while I hide this menu bar that's in my way. There we go. Dr. Sean Liu started his career in drilling and completion fluids at Sueco and has been in various roles in R&D, product development, and technical service at Weatherford and QMax. He is currently working at SciDev for fracturing applications, also as a drilling fluid specialist on drilling fluid projects, including the use of GTL synthetic systems. Sean holds a doctorate degree in chemical engineering with a focus on surfactant applications from Columbia University. Welcome, Dr. Liu, and welcome, Frank. Before I hand over the screen to you, I do want to remind the audience, both guest speakers will be presenting for about 30 to 35 minutes on the technical presentation. During this time, I ask the audience to please place your questions and comments in the chat feature in Zoom. And after the presentation, we should have about 15 minutes of interactive Q&A to address those questions and comments. So please be sure to place those on the chat feature, and we'll be more than happy to bring them up and address them directly with our speakers at the end. Now, with that, Sean, please take it away. I'll stop sharing my screen, and you can start sharing.
Sean, go ahead and put the presentation up.
Sean, are you going to share your screen?
Yes, give me a second.
There we go.
Let me go back to the first slide. Good morning, everyone. Thank you for the introduction. Do you all see the slides okay?
Yes, you're good to go. You're good to go.
All right. Frank, you want to
so basically I'm going to have a very small role here in this presentation. Just for the matter of continuity here, we're going to just, Sean's going to go ahead and present the data on this paper that was written on Shale Organic Matter Interaction with Non-Aqueous Drilling Fluids. And a few, just to give you a little bit of a background history, go to the next slide, Sean. So a little bit of the background. Well, first and foremost, we want to thank the participants in putting this study together. Shell and Patera, Shell, Don Van Slyke, and Patera was Tom Wagner and Buddy Wiley were the participants in this study. And so there was a lot of takeaways from this study. And, you know, this is probably one of many other papers that will still need to be written based on the findings from this study, because it was a very interesting study at the end of the program. So a few takeaways is that, one, there was a development of a test that we were able now to at least test compatibilities between the drilling fluid and the formation. So where in the past, it was really difficult to understand what that compatibility, there was really no API test or a known test, which we were able to test drilling fluids and the compatibility of the formation itself. So out of this, and Sean will go through this overall protocol, but we feel like we've developed a test procedure that will enable us to evaluate compatibilities between drilling fluids and formation. And of course, the interaction of what this paper is basically focused on is the organic matter and how the interaction between non-aqueous drilling fluids interact with some of the disaggregation that occurs during the drilling process. And the whole premise of this study was basically a method of, as we were evaluating the particle size of the drilling fluids as they were being brought back to the surface, is what there was a discovery, or there's a tremendous amount of drilling finds that you're not able to remove with any kind of method, whether you allow the fluid to set and allow it to settle, or go through a centrifuge and try to remove some of those solids. These solids become really, really small, less than 10 microns in size, and are difficult to remove by any mechanical process. So in order to try to eliminate the dilution process and the cost of dilution and the cost of slowing the drilling process, we're able to now evaluate how that fluid and drilling fluid and formation are going to interact, and how those finds are going to be created, or whether there's any finds that are going to be created. And that's the whole process here. The whole purpose is to introduce a new drilling fluid as well as a new testing protocol, and how that interacts with the organic matter. And this basically here is focused on organic matter, not necessarily focused on mineralogy of the formation. But I think a lot of people overlook the organic matter and the compatibility between the OBMs that are being used in the drilling process. And again, as I mentioned, is a way of eliminating the low gravity solids that cause detrimental impacts to both the drilling properties, which include high viscosity and, of course, other drilling issues. The higher the viscosity, the higher the ECD, the greater the drilling problem, and probably the slower rate of penetration that you get. The goal here is to study the role of the organic matter, as I mentioned, in the shale formation during the drilling, as the TOC can be related to the particle disaggregation depending on the base oil types. And I think Sean is going to focus on the various oil-based types and how they interact. So with that small introduction of the paper, again, we want to thank you for your time in participating in the NSI presentations. And Sean, go ahead and present the data.
Absolutely. Like Frank mentioned, we appreciate the host give us the opportunity to present study. We certainly appreciate all the sponsors from Shale, Premier side, and Coterra for us to have this opportunity to work on this project. It's been, I think we started more than 2 years ago. Like Frank mentioned, this is not a API test. We actually developed this test while we were doing the study. As Frank mentioned, this seems to be a drilling fluids application. But if we, go to, 30,000 mile view, and to see overall for drilling, for completion, we always look at the fluid formation interaction, right? So we focus on the chemical we pump, we focus on mineralogy. One thing we learned is the organic material, right? That's exactly what we are drilling for, right? So hopefully this, maybe help some of you, not only from drilling fluids aspect and also from a broader drilling completion fluid aspect, to see how the organic material actually interact with the chemical, either aqueous or non-aqueous, to the formation. Again, this study is focused on the performance of drilling fluids, how they interact with formation material. So coming back to the drilling side, and I don't know how many of the audience on the drilling fluids versus other area. So one of the significant change is the pad drilling in the last 5 to 10 years. The drilling rate of the ROP has doubled or more than doubled, right? But the way we make our mud or we do the solid removal has essentially not changed that much, right? In other words, the technological advancement on a different area are not exactly the same way. We can drill long horizontal wells now, but on the fluid side, we feel there's more studying to be done. And also on a broader background, most wells are still drilled with diesel or oil-based mud, right? So one of the study we're here is, as in the introduction part, we're working closely with the Shale. One of the product we're talking, the gas to liquid GTL, and the GTL has gained a lot of attention in the last 2 or 3 years in many basins, mostly in DJ and Hansville, right? So that's one background here. So one thing we want to start is look at the drilling fluid properties. And one thing we know is everybody, when you start drilling, we're fighting against the drill solid. The reason because when you have solid in your mud, the fluid property go out of range, right? Especially viscosity. One reason is the particle size. When we're drilling, we're getting cut into the fluids, and some of the fines stay in the fluids, like showing here. This is an example of a 14-pound non-aqueous drilling fluids. If you look at the particle size distribution, and the D50 is 7 micron, right? So why that is an issue? But if you look at, again, this is middle school physics, right? If you look at particle size, what's surface area, when you go lower or smaller in size, your surface area goes exponentially, right? Well, that's a demonstration. And when you have more surface area, it consumes more chemicals and it creates more chemical interaction, with the emulsion, with particles. That's the reason we have the issue, right? So certainly there are there's many angles to look at it, because one of the challenges in not only just in drilling fluids, in pretty much in all our operation, we have too many moving parts, right? So, it's very hard to get apple-to-apple comparisons. Okay, what is this or that? When you change too many parameters at the same time, it's hard to get a clear picture. So we feel like we're blessed to able to get some standard material and with standard procedure, but with a non-standard test, right? So we'll go through the test procedure or matrix we were using in this study. Oh, by the way, we published this study in a AED conference early this year that was held in Midland, West Texas. So in case some of you try to take notes, that paper is publicly available. You can look at AED website to find that paper. It has most of the details we're presenting here. So coming back to the test procedure, right? Again, we did more than what we showed here. We feel we just select a part of the data to support our conclusion here. So we select those two samples, right? Basically two core sample or shale samples here, and then we certainly we ground them into fine and versus larger particle, basically 5 to 10 mesh. What we're trying to simulate is the fines that will stay in the fluids. In other words, your solid control equipment cannot take them out unless you do something special like high velocity centrifuge or something. The other one, the cuttings, where you would recover from your shale shaker. The question is how much fine versus larger particle you will get. So before we go that, like Frank mentioned earlier, we all do a lot of study on immunology to look at how much clay, what's the overall rock properties. But at the same time, I think we should look at more on the organic material, organic matter. One of the way to measure is the TOC. So those two, sample A and sample B. So sample A actually have very high organic content, organic materials, like 17.9%. Sample B is 8.7. Certainly, you may argue, is this representative or not? So we've looked at some of the data. Certainly 17.9 is definitely on the high side, but in a lot of US bases, we see average maybe around 4 to 5, and some as high as 8. Right, so like sample B is the core sample we got a hold of. So certainly it varies from formation to formation, from depth to depth. But we think with those, it'd be a good study for us to look. So this is before we go. This is the particle size distribution of the fines. So this is the background. So this basically before we add the dry particle to the fluid, so we know where we started. And so we use this for comparison to see how much the particle size actually changed, right? So this is the test matrix. So if you are familiar with the API 13B2, which is non-aqueous drilling fluid test procedure, a lot of stand tests you basically do a mud check, right? You have your fluid properties, rheology, high temp. Certainly we are following that, but what is new here is what we call accretion test or shale recovery test, right? This is very similar to the rollover test, we do for fracking, but this is for non-aqueous fluids. So the coming to the point, normally we don't think non-aqueous cause any shale issue, and certainly it does not, right, in most cases. But when we look at the drilling, when you have a more movement, when more dynamic force involved, and the property of the non-aqueous fluid matter, right? So what we look at is what the continuous phase, basically the base oil you use make a difference. Right? Again, this is the test procedure we look at. We add the fine to look at how the fluid property change. And then, so this is basically the key of the test, right? We actually have a 1x4 steel bar when we do the rolling test, right? So basically we are simulating the drilling process. We put in the aging cell with the solid, with the 510 mesh solid, and with the fluid we made. We put in the oven and roll them at a temperature, right? So basically we are not only just hot rolling the fluid, we are creating interaction between the steel bar and the fluids, right? So again, the purpose is simulating the drilling process. And when you have a drill pipe, rotating in a hole and under temperature, and you see what happens to your drill cuttings, right? Because depending how deep you are, it may take 1 or 2 hours for the cuttings to move from the bottom to the surface before it get screened out or taken out by the shale shaker. So again, in terms of fluid properties, we are all following the standard API test, but the creation of shale recovery is what we think is new here. So again, like I mentioned at the very beginning, there's too many factors, and a lot of times when we make a mud, it's like cooking in the kitchen, right? So you have to follow some of the standards. So what we did is we certainly started with the standard formulation, right? So all the additives and the formulation we maintain almost identical. What we are varying here is the base oil. I just mentioned a moment earlier. Certainly the oil-based mud is the diesel-based, right? And the synthetic is the GTL, it's new flow based. We're using the identical formulation. We look at the difference. So the question is why the GTL, why new flow? What we think is, the environmental aspect, I don't think we need to even discuss, right? The synthetic or the GTL is pure synthetic and much more environmental friendly. If you're a mud engineer, you know how the feeling standing on top of an oil-based mud pit, right? So me have personally standing on that and also on the mud pit with made of GTL, and you will notice the difference, right? But in addition to the environmental HSE aspect, from the chemical point of view, if you look at diesel, there's a lot of VTEX aromatics, and other diesel always have higher solvency than GTL. GTL is basically a pure paraffin, right? So we don't have some of the data with here, but one example would be the elastomer compatibility, right? So that's another angle. But again, here we are looking how the base oil interact with the material, with the formation material, to see how they impact the fluid properties. So this is the first set, right? This is basically we add the formation solid, and we look at before and after, right? So the key message here, some of you, if not familiar with the rheology property, which will only look at the PV and the YP and the LSYP, basically this is the FAN 35 standard rheology test, which look at the difference between oil-based and synthetic-based. When we look at the properties, and that gives you some indication of how the fluid property will change. Again, viscosity is our enemy nowadays when we're drilling in the US basins, because we have too much solid coming to the fluid. And then this is the HTHP, right, with we call the Shale A fine. As a reminder, this is the one that has 17.9% of organic material. And if you look at the filtration volume in terms of the filtrate, they are very, very similar here. One thing I want to point out is the color And that's an indication of the solvency of the oil-based mud versus synthetic-based mud, right? So one of the reasons we did the filtration is we want to study how you would form a filter cake during drilling, right? I think this is a very interesting slides or some data, right? So this relates a lot of drilling operation where you are tripping or you are running casing. You know, sometimes you have more torque or more friction. You know, even in oil-based mine, normally people think lubricity not an issue. So this may be an indication. So again, so this is after HTHP filtration. We got a filter cake. We just simply roll a steel bar on the filter cake, and what we call the stickiness. And you can see, visually can see the difference. We also measure how much is stuck on the steel bar, and that's a huge difference. This is on the filter cake, right? So now comes to the, I think the most exciting part is what we call the accretion test. This was shale A, and we put, this is, again, it's a 510 mesh solid, and we load them into the fluid. Again, the fluid is we made in the lab, it's a standard formulation, and we hot roll in 250 for basically 3 days, right? And this is one of the results, right? So we're looking at the picture on the top right. This is after we recover the steel bar in the rolling cell, and look at how much some of the solid stuck on the surface. And basically, when we did a comparison, there's almost a double amount of solid stick on the steel bar. And then that's what we see with the shale A, right? And one of the question will be like, okay, this is with one, what happens with others? So we actually did more than just A and B. We have, you know, C and D. Again, for time constraint, we're not showing that data. But certainly we did the same thing with shale B that has about 80% of organic material. We kind of show similar results. But certainly because of clay content, and that is also a factor to your fluid property, right? If you look at here, all the black line, the solid and the dotted line are the oil-based mud. The blue line are the synthetic-based mud, right? So that's basically showing you the same conclusion as we did with shale A, but the difference is that the synthetic mud has much more tolerance to solid when you add fine. So again, as a reminder, this is two separate tests. When we do the fluid property test, we're adding the fines. We're assuming that when you have fine left in your fluid, you know, accretion test, we're using the 510 mesh solid. So this is another angle to look at. This is the particle size. Remember, we did the baseline dry after and before and after hot rolling, right? So here, what we're showing is the change of the particle size, and that's an indication of how much solid could be left behind in your fluids. So make it either hard or easy to recover during the solid control process. So we did the HTHP as well, and this is the filter cake. And again, it's very similar to what we did for sample A. So what we did more on sample or shale sample B is look at the chemical composition change, right? So we, as you know, during HT to filtration, you collect filtrate, right? Basically, I can show you in the previous picture. You see the color difference between the filtrate from the synthetic versus diesel. And also we actually run a chemical GC. Basically, we look at the chemical composition of the filtrate to see if there's any change, right? So because it shows the exact chemical composition, we're not showing the spectrum here, but here are the key takeaways from that study. And we see the amount of volatile, or more specifically, we're looking any peaks on a molecule that less than say 10, basically 10 hydrocarbon, 10 carbon chain, right? So certainly we see how much it changed in oil base. Again, we compare to the virgin fluids, right? The diesel and the GTL, and we see how much it changed. So that's an indication of how much the smaller molecule actually got stuck with the cuttings or with the solid. And because diesel has more of the volatile or the BTX that are less than C10, and those cause more, we can call it incompatibility in a sense. During drilling, that's the reason we have more problem when we have fine solid in diesel mud versus in synthetic based fluids, right? So that gives you kind of a chemical explanation of what we are seeing here. So come back to the shale recovery test. So this is what we did with the shale B, right? So what we did, not only just look at how much stuck on the surface, we're looking at how much we can recover, right? So this is the result, right? So again, we're doing the same, very similar test like we did with shale A. We add the 5 to 10 mesh solid, and we add a certain amount. And after 3 days rolling with the steel bar, we see how much we can recover. So the picture you're showing here is showing how much we recovered on a 5 mesh screen, right? I'm sorry, the 10 mesh screen. We're using the 5 to 10 mesh solid. This is the 10 mesh screen. I mean, visually you can tell the big difference, right? Actually, we did more than one test. When we first saw this result, I was like, okay, that's too much different, because normally we don't think the oil-based mud will have that much disaggregation of a solid. So we had to repeat the test, and that's the number shown on the table on the bottom left. You see how much recovered, in diesel versus synthetic based mud, right? I mean, 98% versus 24%. I think that is huge. I mean, that explains a lot of things going on in the field. For example, you would have to have more dilution with diesel because you have more solid, and the solid removal efficiency, also how dry is your cutting, the mud on cutting ratio. I think this all have impact, right? So for comparison, we did a water-based mud as well, because people always think, oil-based mud should be very inhibitive, shouldn't be any problem. Certainly, when we repeat the test with the water-based, we essentially recovered almost nothing, right? 3.5% is almost nothing. But oil-based mud is only at 24.2%. Again, as a reminder, for this solid, we have 8.7% of organic material, but we do have almost 25% of clay, right? So certainly, depending on the amount of clay and depending on the amount of organic material, and that's showing the impact on the drilling performance. So certainly, if you have more stuff coming to your fluids, and you're gonna see other performance issue like your ROP, your hole cleaning, the casing running, the torque, and you may get more chance to stock. And so this is the fundamental understanding why we are seeing this, right? So again, talking so what is the implication? And certainly we can easily connect this to just the drilling operation, right? So I think I don't know if I did a good job on drawing a shield shape on the bottom, and that's just illustration to see how and what happens when we have a solid or cutting coming from downhole. When it becomes smaller solid, they're going to stay in fluids, right? Like I mentioned, the API, the barite 74 micron. What mesh screen you're going to use, right? You're going to use 100 mesh or 150 or 200. That also cause other problem, right? So certainly we want the cutting to be as large as possible. That way we can recover them. Also, you may have some other issues like been seen many times. When you have fine solid, your fluid problem out of range. You have to keep fighting to keep the viscosity in line. A lot of times the dilution is the solution, but you will end up with more volume of the mud and more cost to treat the material. I'm sorry, to more material to treat the fluid, right? So again, if we take this to the overall, upstream or drilling completion, I think this just give an idea how this material interact. Certainly, the other aspect is the force, right? If you are just pumping, we will not have that much force, but you are drilling, there is a mechanical aspect as well, right? That's the reason with this accretion test, we have the steel bar to simulate the drill pipes, right? So that result in this. I mean, when we saw the result, we are really shocked to see that much difference between the GTL fluids and oil-based mud. So certainly the question is, do you see this in the field? And we've been working with several partners, and we are still looking that at the moment, and that's actually helped to understand a lot of application right now, actually, because when they see something going on, and it's connect back to this study, certainly it was like, do you see this much different in the field? You know, again, like I mentioned at the very beginning, that a lot of moving parts when doing drilling operation, when you really see an apple to apple, like exactly identical well design, and you know, but statistically, when we look at overall performance, we see, you know, for example, the IOP, we see 15% higher with the synthetic fluids. And in terms, I mentioned already, the elastomer compatibility, and we see the lifetime of the mud motor and doubled or tripled because you switch to the synthetic fluid. Certainly the solid recovery, and in some cases we heard you have much less pollution with the synthetic fluids than diesel. Again, you know, we're not trying to say, you know, diesel is bad. I think diesel is bad in terms of the environmental aspect for sure, but, you know, I think 90% of well or the horizontal section is still drilled with diesel. Maybe there are people us a chance to look, maybe we should rethink about it. How not only just the environmental benefit to say this is not an angle to look at overall performance, and this maybe we should consider better, cleaner fluids, just to help us to do the well, you know, better and faster, right? So just to summarize the study today, we in this study we picked 2 shale samples, 2 formation samples. I think that's the key as well, right? So in a lot of the drilling fluid study, you know, we don't get the luxury to get a formation sample. We only get cuttings. The issue with cuttings is that the cuttings being exposed to fluids already, right? You know, either it's oil-based or synthetic-based. You know, either one, it's already being exposed, and your mineralogy and everything have changed. It may not have the exact same mechanical strength as the formation material, right? So we are comparing the performance of 2 base fluids, and again, we're using the standard mud formulation to compare the performance. And the 2 big things here, one is the viscosity. You know, once we understand the interaction, I think the fine solid and organic material is a key factor on controlling the viscosity or rheology of the fluids, because a lot of times when we get the organic material, you know, dissolved, I keep saying diesel have more higher solvency, right? So that is I think that's the key issue, because the high solvency, it dissolves all the organic material in the fluid, and that creates more chemical force. Essentially, you know, all the non-aqueous fluids it's an inward emulsion, right? You create more chemical force, emulsion becomes tighter, your fluid viscosity goes up. So the takeaway message, what I hope is everyone go home with that image I showed in the previous slide, right? You see what is impact on the solid disaggregation, right? So when you have the mineralogy shale, maybe look at organic material as well in the formation, and that explain why we have a poor solid recovery in some of the cases, why you have to use a tighter screen versus larger screen. And again, and more work is more energy, and that's less efficient, that's less efficient. And so hopefully this provides something, for you to take away, take home. Maybe you can use this for other study. Like Frank mentioned at the very beginning, we think this is a pretty cool study. We did this at a premiere, and certainly we couldn't finish this without all the honor sponsors from Shale, Coterra, NSI, and the premiere. So I'll stop talking. I think I finished my goal, Dante.
You're right on time.
2 minutes ahead of
Maybe 2 minutes ahead of time, but that's not a problem. Well, thank you very much for sharing this very interesting studies and very interesting results here for from a drilling perspective. We do have a few questions. The audience is a little light on questions, so I'll give them an opportunity to add some more questions to the list. But let's get started with the first question from Glenn Benj. He's asking if you have any plans to work with API to move this particular testing procedure that you're recommending into a standard test protocol.
That's a very interesting question. I think we should. I have not had any discussion with API yet. Me personally, on the API 13, chapter 13, I'm a member of that. I think I should bring this up, maybe talk to some of the key members to see their feedback. But it's a very good point. I'll take a note on that.
Very good. Now, you did show some results with the accretion test specifically that showed more solids were being dissolved into the oil-based mud versus the synthetic-based mud. And you also showed a slide where you're measuring the viscosity, I believe, and the density. So this dissolution or dissolving of these smaller particles into the mud, it's causing an increase in both density and viscosity, I would assume, right?
So the density, because you have your solid there, right? Density normally is controlled. Certainly density is a critical factor when you're drilling. So to answer your question, it increases viscosity, but as long as you have the same amount of solid in your fluid, your density not really change, right? For example, if you are drilling with a heavy 14-pound mud, most of your density comes with the barite you add. Your low-grade solid actually does not change your density that much. It's almost like secondary factor. That makes sense?
Yeah, no, that makes perfect sense. And that was going to lead me to the question about, I think you alluded to it a little bit, but cuttings transport. I think there's different schools of thought when it comes to drilling. Some people like to drill a very clean hole. Some people believe that you should drill as dirty of a hole as possible. But with the difference in viscosity and difference in cuttings transport characteristics, is this recommendation of using synthetics-based mud the same recommendation across any type of unconventional application, or is it limited to certain specialized applications?
The short answer is we should push for anywhere we're using diesel, right? So there's really not selective to any formation. What we're trying to say is when you have higher organic material, you may have more issues, right? And also when you have a more high clay content, because we know when we're drilling, sometimes we just have issue in certain formation, right? Once you drill through that layer, everything seems to be fine, right? So that's a very good point. So we see more application in DJ and Hanceville, like I mentioned. I think for DJ, there is the environmental aspect. For Hanceville, certainly there's a temperature aspect. And I have a personal work on project in Midland using this. So certainly there is a cost factor into this. People say, okay, so this is a premier fluid, is more expensive, and you'll be surprised to see the benefit you get versus the cost, right? So one thing to add here is, when you use this, you have much better control on your fluid, right? Just to your question, do you want to have a clean hole? You have a dirty hole? I think the reason, because sometimes we don't know what we have in the diesel-based mud, because it's being used again and again, right? You never see a brand new mud come to your rig because there's a history, and the business model is more rental business model, right? You get the mud from somewhere, and then you start using, and some of the drilling engineer believe you have more circulation. So again, the point is, sometimes when you have more circulation, do you actually cause more issue, because the solid, every circulation, the solid becomes smaller and smaller. And when you see a cleaner hole, sometimes you have a cutting accumulation or cutting bed on your hole at a certain angle. That might be the issue, because sometimes when you see the issue running casing, is that because you have too much fine or you have a dirty hole? I think that's the angle to look to answer that question. In particular case, we know when they are comparing these two fluids, the torque or the force to pull the running the casing, it's like over 100,000 Newton. That's difference, right? We're talking about 30% difference in one case.
Yeah, no, that makes sense.
Yeah.
Now, Sean, you mentioned the keyword temperature, and I think that that's a question that I had in my mind. Is the temperature application for this synthetic-based mud still the same as oil-based mud or traditional diesel-based drilling fluids?
Absolutely, I think it actually has more advantage at higher temperature because at 250 that covers most of the basin except some of the Eagle Ford in Haynesville, right? Because at 250 you're not pushing everything to the limit, right? For example, when you look at the organic material, they are hard solid at ambient temperature, but when you push them 250, 350, they become soft, right? Some of the organic material may become liquid. I think that's one of the aspects to look at. I think that's the reason it has more success in Haynesville. Now we are seeing 350 or higher, 370, 380. So to answer your question, it's not really depending on the temperature, but I think we're gonna see more difference, more performance increase when you use at higher temperature like 350. The other aspect to add is the chemical we use. So like I mentioned, making mud is really like cooking in the kitchen, right? When you have to know how to cook your fluids, and a lot of the chemicals, because of the diesel, has more solvency, and it causes more detriment effect on some of the salt, on some of the additive you add. You have to keep adding more solid. It becomes sacrificial, right? When you're drilling. So with synthetic, you still have to maintain, but the consumption or dilution, everything will be less. Again, I think the difference will be bigger at a higher temperature.
Very good point. Now, there's a question that is a little bit more on the fundamental level, and it's coming from Albert Miande, and he's asking, what do you miss when drilling with water-based mud in comparison to oil-based mud and synthetic-based mud? And to add a little bit of context, and correct me if I'm wrong, Sean, but water-based mud is traditionally used only for the vertical section of the well, the non-target portion. And once we turn the corner and start drilling the lateral in our target zone, our organic-rich area, you don't want to use water-based mud because it's going to damage the formation, plug up the pore throats, etc. So you're using an oil-based or synthetic-based mud to prevent that formation damage. Is that correct?
Absolutely, yeah. So
yeah, go ahead.
So the water-based so certainly there are some discussion. You see a lot of study. I mean, not new, right? It's been since 20, 30 years ago, what they call the high performance water-based mud. When you add more shale control material, for example, amine-based, and you try to match the performance of oil-based. But the reality is you have too much water in the water-based mud, right? That's why I call it water-based mud, right? And during drilling, right now, I think the primary goal is you want to drill a 10, 20,000 feet lateral within, we're talking 5 to 10 days, right? So time is money. So in terms of chemical, unfortunately, I don't think the chemical we have in water-based side can match. One is the lubrication. I think in some of the fluids in certain area can do really good job, but overall by average, it still cannot match the performance. I think that's the reason you can continue to see the lateral being drilled with oil-based. I know there are some successful story in certain area being drilled, even the lateral drilled with water-based.
Yeah, well, that makes perfect sense.
Yeah.
Now there's another question, and this one's from Steve Cobb. Steve is asking, well, he first says, your early comment is really interesting about ROP increasing by a multiplier over the past few years, while the fluid handling systems have remained the same. Do you see a need to reinvent the well site drilling fluid handling systems as we've done with proppant over the past 2 decades as volumes increase so much?
The short answer is yes, right? Certainly, I don't know if I can be an expert on the solid removal because there's the mechanical aspect, how you handle. I think the key change a few things. One is the volume of the fluid, right? We are pumping through a longer lateral. I mean, again, depending on the hole size, right? I mean, you're drilling a slimmer hole or a big hole, and with IOP, the amount of cutting comes to the fluid. When we double, triple the IOP, that means we have double, triple amount of solid coming to the fluid, right? but the mud pump has not really changed that much. We're still pumping at, depending, right? Some of the area we're pumping maybe up to 15, maybe maximum 20 barrels per minute. But, some will still add 6 to 10 barrels per minute in that range, right? So how can we effectively take the solid out? I think will be the key, right? So the study we are looking at here is the how much the solid change from the chemical aspect, but from mechanical aspect, like at the diagram I show here, if we have a magical shale shaker that can take the solid out, certainly the other aspect is barite, right? A lot of times we have a barite, and barite has some fine comes in as well. And a lot of the challenge in terms of removing low gravity solid, you don't want to hurt your barite because you don't want to take the barite away. If we have something that can selectively only take the low gravity solid out, but not touch the barite, I think that would be golden for the drilling fluid application, right? If you have a device, and like the question, reinvent the process, something only selectively you take the cuttings out, especially the fines. The other angle is if we have something that can magically glue the fine solid into big ones, and that can be easily removed by the shale shakers, right? I don't have an answer on that. I mean, that's my wishful thinking. So that is another angle, right, from the chemical. If we don't have to reinvent the shale shaker, but if we have something to keep the solid, it's almost like a flocculation in the water base, right? If we can invent some kind of flocculation in oil base during drilling, that will be a winner. I don't know if that answered the question. Yeah.
Oh, I think it does. It sounds like a pretty good challenge for those who are in chemical engineering to see if they can come up with maybe a fluid conditioner or an additive that's added while the fluid goes through the shale shakers and can make this flocculation of cuttings.
Yeah, I mean, don't get me wrong, there has been a lot of new technology, new equipment run out in that space. But again, what I'm talking is the relative change, right? Do you increase efficient by 100, 200%, or about 10, 20%? That's what I meant, yeah.
Yeah, no, perfect. Now, moving on to the next question from Cesar Tunjar. Cesar is asking, can you please elaborate your thoughts about near wellbore skin damage induced, the differences between using water-based mud, oil-based mud, and now this synthetic-based mud? Is there a significant difference on that near wellbore skin damage caused by difference in the fluids?
That's an excellent question, right? So coming back to the earlier question on the water-based mud, right? Number one of the key thing we don't want to use water-based is, water shale interaction. You cause a problem, and that will hurt your production or cause formation damage, right? Because once you water in your formation and then, damage, you cannot even do anything, right? So that's the primary concern. Even with the shale control material, the question is how long you can protect your formation, because after you drill, let's say it's 2 weeks, you're done, but your production will be, years, right? So how that, on the skin damage, again, I think there's difference between conventional versus unconventional, right? So certainly the conventional, you can do a lot of remediation or removal, and that is different. If we're talking, unconventional, and a lot of time people say, hey, I'm going to frack the well anyway, how that even matter, right? And then that'll be the argument. So that's the reason I said earlier, when you drill with water-based mud, more concern is how can I drill my well within the time frame? That's the reason, water-based mud is not there yet. So coming back to the question on skin damage, even on the unconventional, I think there are enough fluid invasion into your near wellbore, right, during drilling, right? That's the reason we're using calcium chloride as internal phase. We're trying to prevent water going into your formation. Coming back to the difference between the oil-based and synthetic-based, we actually did more study on the, shale interaction with just fluids, right? What the thought process is that when you have diesel, you are getting a solvent into your formation, and it can cause more interaction. Again, it's not as magnetic as when you have water there, but it's all relative, right? I think I'll get an example, maybe I get help from Frank, is when we do the permeability study with any shale, what solvent we use to do the baseline? Why don't we use some higher solvent, say oil, to do the initial perm study? So while you can use a more like a non-polar fluid to do that, I think that'd be a I think Frank is expert on that. He can explain better than me. I think that's the angle to answer the question, right? So certainly if you have the frac design, you're really doing concern about skin damage, then it may not be an issue. And the other point to add is the filter cake. I think I showed in some of the slides. I think the quality of the filter cake is not really skin damage, but it can cause some other issue. For example, when you do perforate, where does the mud cake gonna go? They're gonna stuck somewhere, right? And they're not gonna be just magically disappear. They may not go very deep, but they will be somewhere on perforation, and that alone can cause more. I think that can cause more issue than the traditional or the conventional skin damage. Does that answer the question? Frank, you want to add anything on this question?
No, I think, I mean, I don't think I can elaborate any more than you've already elaborated on that. Now, the one thing though that we do need to focus on, I mean, yeah, formation damage or near wellbore damage is one thing, but when we're talking about disaggregation in the immediate wellbore, we're also things that we quite haven't focused on yet, but we need to focus on, which relate to fracturing and cementing, is that you have a better, cleaner hole, a truer hole for better zonal isolation and better fracking isolation, to where when you do go in, you know, it's quite possible that we don't have quite as many communication between zones, between stages. So the better the hole, the better the isolation, the better the stimulation.
Frank, you just lead me to my next question. That was going to be about the impact on cementation. And obviously, you just addressed it. If we can make a better hole and have better cement quality, we get better isolation. Better isolation means better stimulation, and better stimulation leads to better production.
Yeah. So, and wellbore clean out, you're reducing the viscosity. You're not having a big impact with these fines to create this higher viscosity, higher rheological characteristics. So now your ECDs, you don't have to worry about ECD. You can get the velocity that you need to get the hole cleaned out. So, it's a win-win all the way around from a drilling perspective, formation damage perspective, truer hole, and better stimulation practices. So it's an exciting test. It's an exciting fluid. I think it's just, I think it's good to just share with the industry what we have here, and then, that's how you improve things, is that you perfect it. People come in with better ideas and other methodologies and in utilizing this technology, and we move forward.
Absolutely. And to wrap it up with one last question, it's kind of an open-ended question because you have addressed multiple things in this question. But I think the remaining concept to talk about is the cost, right? But what's the cost benefit here? I'm assuming, I might be incorrect, I'll let you answer, but I'm assuming synthetic-based mud might be a little bit more expensive than oil-based mud. If it's not, then it sounds like a home run. But even if it is a little bit more expensive, given all the advantages and benefits that have been discussed, can you talk about that value proposition and give us an idea on the cost differences?
I think you answered the question right there, in that the fact is that you're not having to go back into the dilution, so you don't have to worry about adding more diesel to diluting a viscous fluid. So yes, it's going to be slightly more expensive, but it isn't that much more expensive. Relatively speaking, the biggest expense to any drilling operation and any drilling fluid operation is putting in a new fluid out to location where you're not already established. So,
absolutely.
So what about last one? I know I said last one was last question, but I just thought about something since you mentioned the biggest expense is rolling out a new fluid system. Can we use all the existing fluid handling systems, or is there special requirement equipment for the synthetic-based mud?
No. The beauty about it is you don't need anything different. Everything is already there. All you need is just the hydrocarbon exchange, a paraffin-based system versus a diesel-based system.
Perfect. All right.
And so to add to Frank's comment, on the cost, depending on who you're talking to, right? When you talk to a supply chain guy, even 5 cents is a lot, right? When you talk to engineer, and you may have the overall picture. So we've actually done some analysis along with the Shale to look at the overall benefit versus what's cost, right? Certainly, even just saving one trip to fix your mud motor, that save alone is way more than the initial start. And a certain like Frank mentioned, the initial start cost is because the business model we have in the industry, right? If you already have mud in diesel mud already, now I have to pay a big chunk out. Certainly, the way we've been working is we're working closely with some of the customer to look at the overall benefit of what's the cost, right? So if you save a day on the rig time, nothing else matters. Again, we are the poor chemical guys. The chemical cost is really only a small part. I mean, if you look at the drilling operation, the chemical cost still only 10% of our cost, right? If you can reduce the overall cost by 10%, then 10% of 10% really doesn't matter, right? That makes sense? Yeah.
It makes sense. And I see Ali Danishi wants to bring up a question. So Ali, go ahead.
Yeah, Frank, I just want to let you know your comments and discussion added a lot of value to the whole presentation. And thank you very much. Your insight was very useful here for somebody like me who was listening and trying to learn. Excellent job, Frank, as always.
Thank you, Ali. Appreciate it.
Excellent, guys. One last question from James Rogerson. Have you conducted any studies using lease crude for a hydrocarbon-based drilling mud?
You say crude or?
Yes, lease crude. So actual oil produced directly from the well to make it into a drilling mud.
So in my experience in the past years, you're pushing the opposite direction, basically. Yes. So basically you are using a really, really bad diesel in a sense, right? Yeah. And I actually did that in the past, and it's very hard to make a good amount out of that. During downturn, people have tried that. And I think the headache is not worth the saving. That's my conclusion there.
And I would add one last thing just to wrap up the Q&A, because I know there's a lot of interest here, but we barely even skimmed on the environmental impacts of not using diesel or not using lease crude, right? So I'm assuming that the synthetic-based mud has significant advantages from the environmental perspective as well.
Absolutely. There are a lot of other discussion. I think Don Vance, like he's in the audience, and he's done some industrial presentation just on the environmental. That's the reason I didn't, mention too much about it. To me, that's a given, right? There's no need to just, So absolutely, that's an excellent point, right? Overall, we won't be green, right? So there's no doubt. Makes sense. Well, unfortunately, we are a little bit over time. So Sean and Frank, thank you so much for presenting this case study and for addressing all the audience questions. And thank you to the audience for participating and engaging with our guest speakers today. We really appreciate your participation and engagement. Before you all leave, just a quick reminder, next week we're hosting Alberto Casero, Technical Advisor Fracturing and Stimulation with BP, talking about the unexpected. What do we know about casing deformation and how to deal with it? So be sure to join us next week for what I'm sure to be a great talk. And last but not least, thank you all again. Thank you, Sean. Thank you, Frank. Thank you to SciDev and Premier Corex for sharing this excellent work. And thank you to the audience for your ongoing participation and support of Witness SciDays. If any of you are interested in sharing a case study or being featured as a guest speaker in a future session, please contact us. Let us know. You can send us an email at info@nsitech.com, or you can also connect with NSI Technologies. Follow us on LinkedIn, and you can drop us a message there. Or you can visit our website, and we also have a how to contact us button on our website, nsitech.com. So multiple ways to reach us. Be sure to let us know if you're interested in sharing a case study or being a guest speaker. Otherwise, I think this concludes week 177, and I hope everyone has a great rest of your Wednesday. This video or the recording of our session will be posted on our website later today, so you can share this with any friends or colleagues that you think might benefit from viewing this presentation but weren't able to attend.
Thanks, Appreciate it.
Thanks, Frank.
Thank you. Thanks, everyone. Have a good day.
Have a great one. Bye-bye.